Hey people, let's start learning for earning.
A conventional solid-state PN diode serves one primary purpose. It acts as a one-way valve, allowing electrical current to flow easily from anode to cathode while blocking it in reverse. But this blocking capability has a strict limit. If the reverse bias voltage applied across the diode pushes past its specific breakdown threshold, the component fails, allowing a massive surge of current to punch directly through the barrier. Because this avalanche is highly localized, the friction generates intense, immediate heat, permanently melting and blistering the semiconductor material. To solve this, electrical engineers designed a component specifically built to withstand this exact thermal stress. The Zener Diode is intentionally engineered to survive reverse breakdown, turning a point of catastrophic failure into a highly controlled electrical behavior. The theoretical foundation for this device was established in 1934 by American physicist Clarence Zener, who mapped how electrical insulator properties break down under stress. Using Zener's calculations, scientists at Bell Labs eventually translated this mathematical theory into a physical electronic component. To understand how this component works, we first have to look at the physical construction of the diode and the quantum mechanics operating inside its core. From there, we can map those physics onto a standard current voltage curve to see exactly how engineers deploy this behavior in modern circuit design. By taking a phenomenon that destroys standard electronics and stabilizing it, engineers created one of the most reliable voltage regulators in existence. The defining physical difference between a standard diode and a Zener diode lies in the manufacturing process of its PN junction, specifically the heavy use of doping. Doping is the deliberate introduction of impurities into the silicon crystal lattice, altering the baseline electrical conductivity of the semiconductor material. By heavily doping both sides of the junction, the depletion region shrinks to under 1 micrometer. This reduced distance concentrates the electric field to an extreme degree. Even at just 5 volts reverse bias, it generates a massive 500 kilovolt per meter field. By manipulating the physical geometry of the semiconductor at a microscopic level, engineers artificially intensify the electric field, creating the exact conditions required for quantum manipulation. At the atomic scale, this intense electric field directly alters the behavior of the energy bands within the materials. Under this massive field, the barrier separating the p-type valence band from the n-type conduction band narrows significantly. This triggers quantum tunneling. Valence band electrons tunnel straight through the barrier, emerging directly into the n-type conduction band, instantly initiating reverse current. The Zener effect is a precisely engineered quantum bypass that allows electrons to flow against standard physical barriers, moving beyond the simple survival of an electrical surge. In commercial manufacturing, the components sold under the umbrella label Zener Diode actually rely on 2 entirely different physical phenomena depending on their voltage rating. Under 5.6 volts, junctions are heavily doped. True quantum tunneling, the actual Zener effect, dominates, exhibiting a negative temperature coefficient. Above 5.6 volts, lightly doped junctions use the avalanche effect. High-velocity electrons collide with the crystal lattice, freeing carriers and creating a positive temperature coefficient. These specific breakdown traits can be replicated in other semiconductor architectures. Connecting the collector and emitter of an NPN bipolar transistor together, for instance, allows the base region to act as a surface Zener diode. But surface structures carry a specific risk. Accelerated hot carriers can inject themselves into the oxide layer above the junction, trapping charges and causing Zener walkout, a gradual drift in the diode's breakdown voltage. Knowing the 5.6 volt threshold tells a circuit designer exactly which physical mechanic is driving their system, precise quantum tunneling, or violent particle collisions. In circuit schematics, this specific behavior requires a distinct symbol to differentiate it from standard components. While retaining the standard triangle pointing toward conventional forward current flow, the cathode bar is modified with bent tips, identifying it as a breakdown device. On the current voltage chart's third quadrant, reverse bias current stays near 0 until hitting the Zener voltage, Vz. The line drops near vertically, proving voltage remains locked while current scales massively. A true Zener creates a rounded curve. An avalanche breakdown creates a sharp angle. This graph demonstrates the exact utility of the component. It transforms an unpredictable surge of current into a rigid, unmoving voltage anchor. Because of this locking capability, the primary engineering application for the Zener diode is operating as a shunt voltage regulator. In this linear regulator circuit, the input voltage fluctuates wildly, but the output voltage across the parallel Zener diode remains perfectly stable. During input spikes, the diode drops impedance and shunts excess current away from the load, protected by a mandatory series resistor. If the current passing through the diode, multiplied by its specific breakdown voltage, exceeds its maximum power dissipation rating, the component will overheat and permanently fail. By wiring a controlled breakdown mechanism in parallel with sensitive electronics, engineers isolate the final output from the noise and chaos of raw power supplies. While providing reference voltages is its most common task, the precise nature of this breakdown is leveraged for several other circuit applications. By placing a Zener diode in series with a resistor, it acts as a precise voltage shifter, stepping down an output signal by the exact quantitative value of the diode's breakdown voltage. When two Zener diodes are wired facing each other in series, they create a waveform clipper. This configuration neatly shears off both the upper and lower peaks of an incoming alternating current signal, modifying the wave and absorbing hazardous voltage spikes. Engineers can also harvest the inherently chaotic collisions of the avalanche breakdown effect to build noise generators, creating ideal conditions for dithering analog signals or generating true random numbers. The predictability of the breakdown threshold makes it a versatile utility for regulating power, for modifying signals, and generating clean data chaos. In 1934, Clarence Zener proved mathematically that the catastrophic electrical failure of an insulator could be precisely calculated and predicted. By heavily doping the silicon to shrink the depletion region, manufacturers create a 500 kilovolt per meter electric field that forces electrons to tunnel through solid matter. This quantum mechanism locks the voltage drop in place across a massive range of current, with the 5.6 volt threshold serving as the dividing line between tunneling and avalanche collisions. The Zener diode is an exercise in rigorous material engineering. It takes the specific forces that cause standard electronic components to violently fail and leverages them to build the baseline stability modern circuits depend on.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.